Empirical and theoretical probabilities. Empirical just means we performed an experiment and we found the probability something happens. Theoretical means in theory. If you do a series of trials over and over again, this will happen. Like if you flip a coin, a two-sided coin, 4 times, you may or may not get 2 heads, 2 tails. But if you do it a million times, chances are it's going to average out to be equal, half and half for each. So let's look at the definition of probability. For probability, I have to fix this first. Probability, anytime you see me write the letter P, capital P, in this chapter or in these videos, that refers to probability. The event that we're looking for is E, the event that we're going to find the probability of. So if you ever see this notation, this is the probability of event E. And this little formula that I made actually works for both empirical and theoretical probabilities. The easiest way to think of it is the desired divided by the total. Everything else is just shorthand that you may or may not see. This N is the number of desired outcomes or number of the times that the event occurs. And then this S stands for sample space. It's the number of possible outcomes. So all the outcomes together is called a sample space. And E is just one particular, or it's either one particular event or several events of a sample space. And we'll do some examples here in a second to show you how this all works. Now this example is from an actual experiment. When you read this, it says blah 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 blah. The question is, what's the probability that the patient will develop severe side effects? So I'm going to use shorthand notation. Severe side effects. So to find that, we need to find the number of severe side effects divided by the total effects. I'm just going to abbreviate a little bit. So the answer is going to be a fraction. So how many are severe? We have 72 that had no side effects, 25 had mild, and 3 had severe. So that tells me that 3 had severe. Now, if I didn't see this 100 in there, which gives me the total number of outcomes, what I could do is I could take the 72 plus 25 plus 3. And if you add those up, guess what you're going to get? You're going to get that 100 if you add them together. So the answer is 3 out of 100. And that answer is definitely between 0 and 1. That is a big deal. So that's just an example of experimental probability. But once again, desired divided by total is a good way to think of it. Now the law of large numbers states that if you keep doing a series of trials over and over again, eventually you're going to get to what you expect to get. In other words, over the long run, the answer is going to be predictable. Like flipping a coin. This is an example of rolling a die. If you know anything about a single die, you know it has 6 sides. 1, 2, 3, 4. That's 5. And then the last one. And for example, probability of rolling a 2. Now you could actually take out a die and roll it 10 times, and you may not get a 2 at all. However, if you could do it 1,000,000 times, chances are you're going to get the same number of 2s as you do a 1, a 3, a 4, a 5, and a 6. So it's all going to even out. So this is an example of the law of large numbers for theoretical probability. So here's what we're going to do. Probability of rolling a 2 is the number of times a 2 is rolled divided by, well, I'm just going to make it even easier. That's just too much writing. What I want to do, I'm just going to use desired divided by the total. because it works. So how many ways can you get a 2? Just that one. That's the only one you have right there. How many total rows are there possible? Or how many outcomes are there possible? 1, 2, 3, 4, 5, 6. There you go. That's how you're doing. There's 6 total. I got them all listed there. How about a 4 or a 5? How many ways can you get a 4? Well, there's 1 there. How many ways can you get a 5? Well, there's 1 there. So there's 2 out of how many total? Well, there's 6 total. So when you reduce that, you get an answer of 1 over 3. Now let's look at this one. Rolling a 1, 2, 3, 4, 5, or 6. So there's 1, 2, 3, 4, 5. There's 6 ways of getting a 6 out of how many total? 6. So in other words, you're guaranteed to roll either a 1, 2, 3, 4, 5, or 6. And then my last example, which I'm going to create some space, hopefully. A little bit here. I thought I had enough, but apparently I didn't. How about not rolling a 1, 2, 3, 4, or 6? So what you could do is, or 1, 2, 3, 4, or 5. So you could take away those checks. So the only possible answer there is would be of not rolling a 1, 2, 3, 4, 5, or 6. Nope, 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 nope. 1, 2, 3, 4, or 5, I should say. I keep saying 6. I don't want those, so there's only one way I can roll another number, which is a 6. Have how many possible outcomes? 6. However, the reason why I have this example, because there's a backwards way to look at this. Or you can find this. Since the total outcome for all of them is 1, I could do 1 minus the probability that a 6 is rolled. I can think backwards. How many ways are there of rolling a 6? Well, I'm thinking wrong. Of not wrong. See, I'm thinking wrong. Yeah. I'm thinking backwards, or I'm thinking the opposite. Maybe a better way to think of it. 1 minus probability of rolling a what? Rolling a 1, 2, 3, 4, 5, or 6. And in that case, you can do 1 minus. So how many ways can you roll a 1, 2, 3? I'm just messing up all over the place. Makes me want to start this video over. But I'm not going to, because I hate starting videos over. So I'll start this problem over. I'm going to back up and repeat myself, or start over again. I mean, on this particular example, at this point right here. Okay. Now, another way to look at this, you can do 1 minus the probability of the opposite of this. And the opposite of this is actually rolling a 1, 2, 3, 4, or 5. That's the word is or. And so how many ways can you roll 1, 2, 3, 4, 5? Well, there's 1, 2, 3, 4, 5 ways of a possible 6. Not saying this is what you want to do. I'm just saying you could do it this way. What is 1 minus 5, 6? So 1 is the same thing as 6 over 6, is it not? Because we already saw that up there. And 6 over 6 minus 5 over 6, which I'm going to write that a little bit better. Because you know, I already have 6 over 6 is equal to 1 up there. So that would equal 1 out of 6 that way. Maybe not the best way to doing it, but you can still do it. A better question might have been the probability of not rolling a 2. So if I were to, let's say I ask you that one. It can't hurt, right? Probability of not rolling a 2. This, you may want to do this. You may want to do 1 minus the probability of rolling a 2. Because we just found out how many ways can you roll a 2? What's the probability of rolling a 2? 1 out of 6. So this would be 1 minus 1 over 6. It's a backwards way. And 1, once again, we've already seen is 6 over 6. And 6 over 6 minus 1 over 6 is 5 out of 6. So that may be a better example for that one. But I'll give you two different examples. Doesn't matter which way you approach it. You'll get the same answer either way. You could easily have done not rolling a 2, which means you roll 1, 3, 4, 5, or 6. There's 5 ways to do that. The reason why I did that example is to show you some of the properties of probability. Because, let's this first example, probability of an event that cannot occur. If I were, for this die example, if I were to ask you the probability of rolling a 7, well, can you roll 7 with a single die? No. Since you can't, the answer is 0. So that's not possible. So event that can occur. So if that ever happens, the answer is 0. You don't say not possible, you say 0. Probability of sample space, what that is, it's all possible events, which is this example right here. That was all possible events or outcomes. And what was the probability for such a case like that? Well, the answer was 1. So that's what that example means. And then the reason why I showed you this example just then and this example and all these other ones, notice all the other answers. We got 1/3, we got 1/6, we got 5/6 as answers. Those answers were all between 0 and 1, and then you can also get an answer 0 and answer 1. So when you do probability, your answers will always be between 0 and 1, and including 0 and 1. So if you get an answer that's negative or bigger than 1, you did something wrong. And then the last example I was doing, it's actually called a complement. The probability of a complement is the same as 1 minus the probability of the event. So that not E is called the complement. So in other words, it's like thinking backwards. It may be easier sometimes to think backwards. A lot of times it is. Hey, 10% chance it's going to rain. You know what that means? It's the same as 100% minus 70%, which is equal to 30%, won't rain. Get that? It relates. It's just thinking backwards. Some people have to always be negative, or unless you like rain, of course. So 70% chance rain. Hey, there's 30% chance it won't rain. Just thinking backwards. Now, with probability, you can see cards used quite a bit, and some people may or may not know the cards, so I've got them all listed right here. There are 4 suits. As you can tell, well, you may not know, these are called spades. And these are black. These are called clubs. They're also black. These are called hearts, and they're red. These are called diamonds, and they're red also. Each suit has 13 cards per suit, for a total of 52 cards. All suits have the same. Ace, that's an ace. Then 2, 3, 4, 5, 6, 7, 8, 9, 10, that's a jack. Queen, king. You may or may not know those, so that's why I'm going over them. The jack, queen, king are the only ones that have faces on them, so these are called face cards. How many of them are there? 13. So we're going to use this information. Notice, once again, half are black, half are red. So we're going to use this to answer some questions. So what I need to do is I need some space. I need space. So let's go ahead and create some space while I'm doing these problems. You can see some different types of examples. Okay, probability of choosing an ace. So once again, I'm just going to use the desired over total on every one of these. So how many aces are there total? There's 1, 2, 3, 4. How many total cards are there? 52. When you reduce that, you divide each of those by 4. That's 1 out of 13. You actually take one suit. You notice you got 13 cards in a suit. And how many of them are aces? 1. 1 out of 13. It actually makes some sense if you think of it in terms of suits and also as all 52 cards. Choosing a red card, all kinds of ways to look at it. 52 cards. How many of them are red? Well, these 13, that's 26. If you reduce that, you get 1/2. You can look at that and see 1/2. You can do this. You got 4 suits. 2 of them are red. 2 out of 4 is still 1/2. All kinds of ways of looking at it. Face cards. I've already told you how many face cards there are. There's 13. Have how many total cards? 15. Then reduce that. You can find out 4 is used quite a bit. So, well, but in this case it's not. So 13, but 13 does go into both 13 and 52. 13 goes in 13 one time. 13 goes in 52 4 times. There's all kinds of fractions in cards, by the way. 13 out of 52 are face cards. Well, I'm wrong. I'm not about to make this video over just for that one mistake. I gotta learn how to count. There's 12 face cards. 3, 6, 9, 12. Which makes it even better. Hopefully you saw that and you already fixed it before I did. So there's 12 face cards out of 52. Do you know how I caught that when I was doing this fraction stuff? I was going to show you that if you look at a suit, there's 13 cards per suit. And how many of them in a particular suit has face cards? 3. So it should reduce down to 3 out of 13. And in this case, 4 divides into 12 and 4 divides into 52. 4 goes in 12 3 times. 4 goes in 52 13 times. So I actually used my fractions to check my answer, because I knew when I looked at my face cards in this particular suit, the diamonds, 3 out of 13. So when it didn't reduce the way I wanted it to, I knew there was a mistake somewhere. So even though I make mistakes, you can learn from them, in other words. So making mistakes in video, yeah, you're probably going to go and make fun of me, blah blah blah, he doesn't know what he's doing. Maybe I'm doing them on purpose. You never know. So you can see how to catch yourself. I am not doing them on purpose. But don't tell anybody that. Okay, now this one. Probability of choosing a king or a 3. Now this one, you got to think about it just a little bit. Well, not really. It's still going to be out 52. How many kings are there altogether? Well, there's 1, 2, 3, 4. And how many 3s are there? 1, 2, 3, 4. So there's 4 kings and there's 4 3s. So that's the same as 4 plus 4, which is 8 total cards altogether. And then you can reduce. Once again, 4 divides in both of those. That goes 2 and that goes 13. Watch this. By suits, 13 cards in the suit. How many are 3s? How many are kings? There's 1, 2 out of 13. That's a king or a 3. I don't know, I may have said something differently, but king or 3. See that? How about not choosing a spade? Several ways of doing this. You can actually count and see there's 4 suits and one of them is a spade. So how many of them are not spades? 3. So if you want to do it by suits, you can do that. So 4 suits. And how many of them are not a spade? 3. So 3 out of 4. Or you could just done this. 1 minus probability choosing a spade. So what's the probability of choosing a spade? Well, 1 out of 4. Because there's 4 suits, and one of those suits is a spade. Well, 1 is the same as 4 out of 4. 4 out of 4 minus 1 out of 4 is 3 out of 4. You don't have to do it this way. I'm just showing you. There may be another way. So whichever way you prefer is totally up to you. And then probability of choosing a red card and a black card. The and means the card has to be both. Red and black. A single card. Both red and black. I'm going to come up here. Do you see any card that is both red and black? Do you see one? I don't see one. See, or means you want it, like in this example, a king or a 3. Either or means you win. On this example, you want a card that's red, both red and black. No such card exists. 0. So you don't say no such card. You say the probability is 0. That's the answer. So, just some examples to consider. And hopefully you've learned a few things. Or you will learn a few things. And you can use this to apply it to more things that you will learn.